When evaluating Roman aqueducts, modern observers often attribute their centuries of endurance to mass and muscle. The assumption is that Roman engineers solved infrastructural challenges by piling on excessive amounts of masonry, relying on sheer physical scale rather than an understanding of dynamic fluid mechanics. This animated diagram illustrates that assumption. It treats the aqueduct as a static, continuous delivery system, a dumb pipe. In this model, gravity simply pulls a constant, predictable volume of water from a source down to a city at an unregulated rate. The historical hydrological data tells a different story. Readings taken from the ancient Roman spring at Gors revealed that the natural output of these water sources fluctuated significantly depending on the season. Looking at this data plot, the flat line represents the theoretical constant flow. The jagged line is the reality. During the dry season, the minimum daily flow of the Gors spring routinely dropped to less than 10% of its maximum wet season output. Subjecting a static, unregulated masonry channel to that kind of variance is structurally fatal. A system engineered for dry season trickles would instantly drown under a 10x volume spike. The water would breach the sidewalls or violently scour the foundational mortars. To survive centuries of these massive hydrological cycles, the aqueducts had to function as dynamically regulated machines, guided by a rigorous, implicit understanding of fluid dynamics. That dynamic regulation is visible in the topography of the Nimes aqueduct. To cross the landscape, the channel had to maintain an ultra-flat gradient, dropping a mere 7 millimeters for every 100 meters of distance. This visualization demonstrates the specific physical threat of that ultra-flat geometry, the backwater effect. Because the slope is so negligible, the water cannot drain fast enough. It pools backward, and the fluid depth increases relative to the bed slope. Left alone, this rising water column exerts critical pressure on the roof of covered channels and easily spills over the sidewalls of open sections, washing away the surrounding soil and collapsing the structure. Roman engineers intervened physically. Upstream of major bridge crossings like the Pont du Gard, archaeological excavations have uncovered specific in-stream regulation basins built directly into the channel path. This diagram details the math behind the two distinct gate types installed inside these basins. On the left is the overshoot or spillway gate, where discharge, Q, is proportional to the head height raised to the power of 1.5. Roman engineers deployed overshoot gates exclusively for overflow channels. Because the discharge rate scales rapidly with height, a small increase in floodwater generates a massive increase in flow rate, rapidly dumping excess storm surges safely out of the aqueduct. On the right is the undershoot or sluice gate, where discharge is proportional to the upstream water depth raised to the power of 0.5. Conversely, they installed undershoot gates exactly at the main canal intakes. By drawing water from the bottom of the basin, the formula dictates that wide fluctuations in surface depth result in only minor variations in output. The flow remains stable. Separating these gate types confirms that Roman architects were actively manipulating fluid states. They split the flow mathematically, dumping the unpredictable volume spikes while feeding a protected baseline rate into the fragile bridge canals. Steep mountain descents present the opposite physical challenge. When the gradient drops sharply, the water accelerates rapidly. As we see in this simulation, gravity forces the water out of a tranquil state and into a supercritical flow. The fluid accumulates a massive load of kinetic energy. Structurally, supercritical flow is a destructive force. Over time, the kinetic energy of the rushing water acts like a grinder, scouring the mortar and stripping the stone blocks from the inside. To strip this energy out of the water, Roman engineers designed drop-shaft cascades, placing them at specific intervals along steep descents, like the aqueduct at Valdepuentes. This cross-section shows the mechanics in action. Instead of allowing the water to gain speed down a ramp, the channel dead ends, forcing the high-velocity horizontal flow to plunge straight down a 90-degree vertical shaft. Hitting the bottom of the shaft triggers a specific fluid phenomenon, a hydraulic jump. The water crashes into itself, creating a turbulent, swirling roller that absorbs and bleeds off the kinetic energy. By the time the water exits the bottom of the shaft, it has returned to a tranquil state. These cascades function as targeted energy dissipators. Roman engineers isolated the violent forces of the water inside dedicated armored shafts, preserving the structural integrity of the rest of the system. Managing the internal forces of the water is only half the equation. The external solid mechanics of the aqueducts required equally exact structural planning. This is the Pont du Gard. It spans the Garden River at an elevation of 49 meters, making it one of the tallest structures built in antiquity. At this altitude, positioned inside a deep river valley, a vertical masonry wall faces extreme lateral wind shear. High-velocity winds apply constant, uneven pressure across the face of the bridge. The macro-level solution is visible in its silhouette. The bridge consists of 60% open space and 40% stone, drastically minimizing the surface area exposed to wind shear. The micro-level solution exists in the geometry of the arches. This diagram highlights a critical choice. The Romans avoided simple circular arches with uniform, easily interchangeable blocks. Instead, they built flattened, elliptical parabolas. To safely distribute weight down an elliptical arch, the load must strike the joints perfectly. This mechanical reality requires every single voussoir, the wedged stones forming the arch, to be cut at a mathematically specific angle. None of these blocks are interchangeable. We know the Romans calculated these angles in advance because the original stones are still marked. Carved directly into the blocks are specific Roman numerals, alongside positional codes for front, left, right, and center. This labeling system dictates that the unique geometry of every stone was drafted and carved off-site. The blocks were transported and slotted into their predetermined position within the elliptical matrix. The integration of numbered blocks and optimized elliptical geometry reveals a rigorous system of geometric precalculation, allowing these architects to stabilize their designs against the severe environmental stresses of the river valley. This level of architectural precision creates a logistical hurdle. The uniquely angled stones of the Pont du Gard weigh up to 6 tons each, and they had to be lifted into position 49 meters above the riverbed. This simulation shows the Roman answer to that hurdle, the polysbaston. It is a massive wooden treadwheel crane designed for high-altitude, heavy-lift construction. By utilizing the mechanical advantage of the large wheel radius and compound pulleys, a crew of just 4 operators walking inside the wheel could smoothly hoist a 6,000-kilogram payload. This data comparison reveals a stark difference in efficiency. Egyptian construction required 50 men to drag a 2.5-ton block up a ramp. The Roman polysbaston used 4 men to lift double that weight, generating a 60 times increase in mechanical efficiency per worker. The success of the Roman water network relies on the integration of these disciplines. They mapped ultra-flat gradients with exact linear surveying, hoisted materials using unprecedented mechanical lifting multipliers, and managed water volatility through dynamic fluid kinematics. The endurance of the Roman aqueducts stands as physical evidence that their engineers successfully navigated these core principles, mastering mass conservation, energy dissipation, and structural optimization centuries before the formalization of modern physics.